parallel port history. At the back of an old beige personal computer, surrounded by serial connectors, keyboard ports, and video outputs, there was once a wide 25-pin socket that almost every user recognized. It was large, awkward, and impossible to mistake for anything modern. A thick cable connected it to a printer sitting somewhere nearby, often beside a stack of paper waiting to become letters, invoices, reports, school assignments, or lines of computer code. For millions of people, this connector was simply the printer port. Technically, it was part of the parallel interface, and for decades, it served as one of the most important gateways between the personal computer and the physical world. Today, the port has almost disappeared. USB, wireless networking, and modern serial links have replaced it. New computers rarely include it, and many younger users have never seen one. Yet the parallel port played a far larger role in the history of the PC than its simple appearance suggests. It began as a practical way to send characters to a printer, became part of the standard IBM PC environment, evolved into a bidirectional peripheral interface, and eventually found its way into scanners, external drives, security dongles, test equipment, electronics laboratories, and home-built hardware projects. To understand why such a large connector became essential, we have to return to a time when computers and printers did not speak through universal interfaces, when every wire mattered, and when moving 8 bits at once seemed like an elegant solution to a very practical problem. Before personal computers became common, printers were already important computer peripherals. Businesses needed paper records, universities needed printed program listings, government offices produced reports, engineers printed tables, measurements, and technical output. Early computer systems therefore required a dependable way to send data from the machine to the printer. The challenge was not merely to transmit the character itself. A printer had moving parts. It had to know when data was ready, whether it was busy, whether paper was available, and when another byte could be accepted. The computer needed a way to coordinate with the mechanism at the other end of the cable. One important influence came from Centronics Data Computer Corporation, a company known for line printers. The Centronics style interface that emerged in the early 1970s became one of the most widely recognized parallel printer connections. Instead of transmitting a byte 1 bit at a time down a single data path, the interface used multiple data lines. 8 separate wires could represent the 8 bits of a byte at the same moment. In simple terms, the computer placed a complete byte onto the data lines, signaled that the data was ready, and waited for the printer to respond. This is where the word parallel comes from. In serial communication, bits travel one after another. A single data line may carry a 1, then a 0, then another one, and so on until the entire byte has been transmitted. In parallel communication, several bits travel side by side. Imagine 8 people carrying 8 boxes through 8 separate doors at the same time. That resembles an 8-bit parallel transfer. Now imagine those same boxes passing one by one through a single door. That resembles serial transmission. At low and moderate speeds over short distances, the parallel approach seemed obvious. If 8 bits could be sent at once, why wait for them to travel one at a time? But the speed came with complexity. A practical printer connection needed far more than 8 data wires. It required control and status signals as well. The computer needed to tell the printer when the byte on the data lines was valid. The printer needed to indicate when it was busy. It needed to acknowledge data. It might report that paper was missing or that another error had occurred. Ground wires were needed to provide electrical reference. The result was a thick cable containing many conductors and a large connector with enough pins to support them. On the printer side, the classic Centronics style connector commonly used 36 contacts. On the computer side, the connector that became familiar in the PC world used a 25-pin D subminiature form, usually called DB25 in everyday usage. The two ends did not look the same, but together they became one of the most recognizable cable arrangements of the personal computer era. The interface was not designed to carry data over great distances. Parallel signals have to arrive with enough timing consistency that the receiving device can interpret them correctly. When several wires run beside one another, differences in electrical delay, interference, and signal quality can become more difficult to manage as speed and cable length increase. In the early years, however, printers usually sat only a few feet from the computer. The cable was short. The data rates were modest. Under those conditions, parallel communication worked well. Then, in 1981, the IBM personal computer arrived. IBM entered a computer market that was already full of different machines, operating systems, and hardware designs. Its new personal computer was intended for offices, businesses, technical users, and eventually homes. Printing was essential. A business computer without a practical printer connection would have been incomplete. IBM therefore offered a parallel printer adapter as part of the system's hardware ecosystem. This decision helped make the parallel port a standard feature in the emerging PC world. The IBM PC itself did not invent parallel printer communication, But the popularity of IBM-compatible machines spread the interface across an enormous installed base. As clones and compatible systems multiplied, the 25-pin printer port became familiar on the back of desktop computers around the world. For users, the port quickly became associated with a simple name, LPT1. The letters LPT came from the historical idea of a line printer. In DOS and related PC environments, printer ports were identified with logical device names, such as LPT1, LPT2, and sometimes LPT3. The first parallel printer interface was generally LPT1. A program could send data toward that device without requiring the user to understand every electrical detail of the connector. That abstraction was important. A person using a word processor did not care which data line represented the third bit of a character. A business application did not need the user to manually pulse the strobe signal. The computer's firmware, operating system, and software environment provided ways to access the port as a device. The physical interface existed in hardware, but to the user, it became part of the software vocabulary of the PC. For an entire generation, commands involving LPT1 were completely normal. Text could be redirected to the printer, applications could open the printer device, diagnostic programs could test the port. The term appeared in manuals, setup screens, and technical support conversations. If a printer did not work, users might be told to check LPT1, confirm a cable, or inspect BIOS settings. Yet behind the simple name was a carefully timed electrical conversation. Imagine a user in the 1980s pressing the print command inside a program. The software prepares characters and formatting information. Eventually, bytes must leave the computer and reach the printer. The PC places a byte across the parallel data lines. Then a control signal indicates that valid data is present. The printer detects the signal and begins processing the byte. It may briefly indicate that it is busy. When ready, it responds through the status lines, allowing the computer to send the next byte. This exchange is known as handshaking. Handshaking matters because a printer is not simply a passive wire. It is a machine with motors, print heads, buffers, paper handling, and internal logic. It cannot always accept data instantly. If the computer sends information faster than the printer can receive it, bytes may be lost unless some form of coordination exists. The parallel interface therefore carried both information and control. The data lines said, in effect, here's the next byte. A strobe or similar signal said, this byte is ready. The busy line could respond, wait. An acknowledged signal could indicate, I received it. Other lines could report errors or paper conditions. This back and forth may sound primitive compared with modern interfaces, but it was effective. For ordinary users, it was invisible. They pressed print, the printer began making noise, paper moved, and characters appeared. The simplicity of the user experience helped make the parallel port successful. It was not necessarily elegant by modern standards, but it solved an important problem with relatively straightforward hardware. Better still, it became common enough that manufacturers could design products around it. Then, something unexpected happened. Engineers, technicians, and hobbyists began to realize that the parallel port was useful for more than printers. The reason was simple. The port exposed a collection of digital signals that software could manipulate. If a program wrote a value to the port's data register, electrical levels on several pins changed. If the program read the status register, it could observe certain signals coming from outside the computer. For someone interested in electronics, this created an inexpensive bridge between software and physical hardware. A programmer could write a byte and turn LEDs on or off. With interface circuitry, the port could control relays. Relays could control motors, lamps, or other electrical equipment. Sensors could feed simple status signals back into the computer. Educational laboratories used the port to demonstrate digital logic. Students learned how software could cause real electrical changes outside the machine. Home experimenters built projects around it because the interface was already present on the PC. There was no need to purchase an expensive specialized controller, just to obtain a few digital input and output lines. The parallel port became a gateway into hardware experimentation. Its usefulness expanded into commercial peripherals as well. Scanners appeared that used the port, external storage devices used it, some backup drives, removable disks, and CD-related devices connected through parallel interfaces. Hardware security dongles were often attached to the printer port. Industrial systems used it for specialized controls. EEPROM programmers, measurement equipment, and diagnostic tools took advantage of its accessible signals. This transformed the meaning of the connector. It had been designed primarily to send data from the PC to a printer. Now it was becoming a general-purpose peripheral interface. But the original design had limitations. The earliest printer ports were largely oriented around one-way data flow. The computer sent 8-bit data outward toward the printer, while only a smaller set of status signals returned. That was acceptable for printing because the printer mostly needed to receive data. A scanner was different. A scanner had to send significant amounts of image data back to the PC. An external storage device needed more flexible two-way communication. As peripheral demands grew, the original port architecture began to feel restrictive. Manufacturers started developing bidirectional capabilities. Some implementations allowed the data lines themselves to reverse direction. Instead of always carrying bytes from the computer to the peripheral, the same lines could sometimes carry information back. This was a major improvement, but it created another problem: compatibility. If every manufacturer invented a different extension to the parallel port, devices could become unreliable across different computers. A scanner might work with one motherboard, but fail with another. A faster printer might require a particular controller. The interface had become important enough that the industry needed more consistent standards. Two enhanced approaches became especially significant: EPP and ECP. EPP stood for Enhanced Parallel Port. It was designed to support faster, more efficient two-way communication with peripherals. Instead of forcing software to manually coordinate every tiny transfer through slow sequences of instructions, hardware support could manage more of the transaction. This made the parallel port more useful for devices requiring frequent bidirectional transfers. ECP stood for Extended Capabilities Port. It was developed to improve performance for printers and other peripherals and included features intended to support more efficient data transfer. Depending on the implementation, hardware mechanisms such as DMA could reduce CPU involvement and improve throughput. For ordinary users, these acronyms appeared in BIOS setup menus. A user troubleshooting a printer or scanner might see choices such as standard, bidirectional, EPP, ECP, or combinations of these modes. Most users had little idea what the settings meant. They simply selected the mode recommended by the device manual. Behind that confusing menu was a story of an old printer interface being pushed far beyond its original purpose. The parallel port was becoming faster, more flexible, and more capable, but the industry still needed a common framework. That framework arrived through IEEE 1284. IEEE 1284 formalized methods for bidirectional parallel communication between personal computers and peripherals. The standard defined signaling behavior and modes intended to improve compatibility across devices and systems. By this point, the parallel port was no longer merely a collection of wires inherited from old printer designs. It had become a standardized PC peripheral interface with several operating modes. This was the technological high point of the parallel port. By the 1990s, the connector was everywhere. Look at the back of a typical desktop PC from that era, and the parallel port is difficult to miss. It usually sat beside one or two serial ports. The serial connectors were smaller. The printer port was wide and unmistakable. On many systems, it was even color-coded later as part of standardized connector schemes, often appearing in burgundy or magenta shades. Printers remained its most familiar use. Dot matrix printers, inkjets, and laser printers connected through parallel cables. In schools, rows of PCs might share similar printer setups. In offices, the sound of dot matrix printheads or laser printers was part of daily computing life. At home, users printed letters, homework, banners, address labels, and early digital photographs. But the port's hidden uses continued. Scanners connected through it. External zip drives and other removable storage products used parallel versions. CD-ROM devices and backup equipment sometimes relied on it. Security dongles occupied the connector and occasionally included pass-through arrangements, so a printer could still be attached. Laboratories used it for instrumentation. Industrial systems used it for control. Programmers accessed it directly from DOS because the hardware was relatively exposed and simple compared with later protected operating systems. For hobby electronics, the parallel port became almost legendary. Tutorials showed how to write values to the port address and make pins go high or low. Small interface boards protected the computer from electrical damage. LEDs flashed under software control. Stepper motors moved. Simple robots responded. Home-built CNC and automation projects sometimes depended on precisely timed parallel signals. The port allowed ordinary programmers to experience something powerful. Software could reach directly into the physical world. That accessibility was partly a product of the era. Early PC operating systems allowed applications much more direct access to hardware than modern systems typically permit. A DOS program could write to an I/O address and alter port behavior with little interference from the operating system. This was convenient for experimentation, though it also meant software could easily misconfigure or crash hardware. As Windows became dominant and hardware protection increased, direct access became more complicated. Drivers were needed. Timing behavior became less predictable. Yet the parallel port remained useful for many years because so much equipment depended on it. Then another interface began appearing. At first, USB looked modest. The Universal Serial Bus was introduced to solve a growing problem in personal computers. By the mid-1990s, PCs had accumulated a confusing collection of connectors. Printers used parallel ports. Modems and mice might use serial ports. Keyboards had dedicated connectors. Joysticks used game ports. Scanners might require SCSI or parallel connections. Some devices needed separate expansion cards. Installation could involve IRQ settings, DMA channels, port addresses, jumpers, and driver conflicts. USB promised a more unified model. One connector family could support many kinds of peripherals. Devices could identify themselves electronically. The system could detect them automatically. Hubs could connect multiple devices. Many peripherals could receive power through the cable. Most importantly, USB used serial communication. This sounds ironic. Parallel interfaces had once seemed attractive because sending several bits at the same time appeared faster than sending them sequentially. But as electronics improved, high-speed serial communication became easier to scale than wide parallel buses over cables. The problem with parallel transmission is synchronization. If 8 or more signals travel down separate wires, the receiver must interpret them at the correct moment. At higher speeds, even small differences in timing between wires become important. Electrical interference and crosstalk can also complicate signal integrity. Maintaining clean synchronization across a wide cable becomes increasingly difficult. A modern high-speed serial link can transmit bits extremely rapidly over fewer signal paths. Advanced encoding, clock recovery, differential signaling, and sophisticated controllers allow serial interfaces to achieve speeds far beyond what the old PC parallel port could practically deliver. USB also had a physical advantage. The connector was smaller, the cable was thinner. That mattered as computers became more compact. A desktop tower could afford a large DB25 port, a thin laptop could not. Manufacturers began removing legacy connectors to save space and cost. Serial ports disappeared from consumer systems. Game ports vanished. Dedicated keyboard and mouse connectors became less important. The parallel port followed them. Printers moved to USB, scanners moved to USB, external storage adopted USB and other high-speed serial interfaces. Network printers eliminated the need for a direct cable to the PC at all. By the 2000s, the parallel port was becoming a legacy feature. Some desktop motherboards continued supporting it for businesses and industrial customers. Add-on cards and USB to parallel adapters allowed older devices to survive. Specialized equipment kept the interface alive, because replacing a working industrial system can be far more expensive than maintaining an old connector. But for ordinary consumers, the era was ending. The disappearance happened quietly. There was no ceremonial announcement that the parallel port was dead. One generation of PCs had it, another generation sometimes did not. Printers arrived with USB cables. New laptops were too thin for the old connector. Users gradually stopped noticing. Yet the port left behind an important legacy. It represents a stage in computing when peripheral interfaces were closely tied to specific functions. A printer port was for printers. A serial port was for modems and other serial devices. A game port was for joysticks. Each connector had its own electrical assumptions and software conventions. Modern computing moved toward universal buses and network devices. The parallel port belongs to the earlier world, when connecting hardware often meant understanding exactly what kind of port a device required. That world may seem inconvenient now, but it was also unusually transparent. The parallel port exposed the logic of the machine. A programmer could understand which bits controlled which pins. An electronics student could measure signals with a meter or oscilloscope. A hobbyist could build an interface with a handful of components and see immediate results. The connector was large because it carried many signals directly. There was something almost physical about the relationship between software and electricity. Write a value. A pin changes state. Connect a circuit. Something moves. That directness helped educate generations of programmers and engineers. The port also demonstrates how technology can escape its original purpose. It began as a printer connection. Then users discovered it could support scanners, drives, security devices, experimental hardware, and control systems. The architecture was not originally designed for every one of those applications. The ecosystem expanded because the interface was available, understood, and flexible enough to be adapted. This pattern appears throughout computer history. A successful interface often becomes useful in ways its designers did not anticipate. Once enough machines include the same connector, manufacturers gain a reason to build products for it. Once enough products exist, users have a reason to keep buying systems that support it. Compatibility creates momentum. The parallel port benefited from that effect for years. Its history is also a reminder that the meaning of speed changes over time. In the early era of computer peripherals, parallel communication seemed natural because several bits could travel at once. Later, faster electronics made serial communication superior for many external links. The physical intuition that more wires must mean more speed turned out to be temporary. Modern high-speed serial buses carry enormous amounts of data over remarkably few conductors. The old parallel cable, once a symbol of speed and practicality, became a symbol of technological limitation. But calling it obsolete should not make us underestimate its importance. For years, the parallel port was one of the essential interfaces of the PC. It connected businesses to printers. It helped schools turn digital text into paper assignments. It let programmers produce hard copies of code. It connected scanners and storage devices during a period when consumer peripherals were expanding rapidly. It enabled hardware security systems. It gave electronics hobbyists a simple way to control the outside world. It taught users the meaning of LPT1. And it helped bridge the era between specialized computer interfaces and the universal connections we take for granted today. There was also a cultural dimension to the port that is easy to forget. A printer was once one of the most important reasons to connect something external to a personal computer. Before email attachments, cloud documents, and digital forms became routine, information often had to leave the computer as paper. The parallel cable carried that transition from digital memory to the physical office. A spreadsheet became a financial report. A word processing file became a letter. A school essay became pages that could be handed to a teacher. Source code became a printed listing that programmers could annotate with a pen. In that environment, the printer port was not a secondary convenience. It was part of the workflow of computing. Even the sound of printing belonged to the experience. Dot matrix printers rattled across continuous sheets. Impact mechanisms struck ribbons. Laser printers warmed up before producing crisp pages. Inkjet printers moved their heads from side to side. Behind each of these mechanisms, bytes crossed the parallel cable in a disciplined sequence of data and control signals. The user rarely saw the conversation, but the rhythm of the printer was the audible result. Technically, the parallel port also represents a period when the boundary between software and hardware was unusually accessible. On many DOS systems, developers knew the conventional I/O addresses associated with LPT ports and could interact with them directly. This made the interface popular for test equipment because a program could toggle lines with very little abstraction in between. Engineers built production fixtures that used the port to program or verify electronics. Laboratories used it to collect simple status information. Amateur radio enthusiasts, robotics builders, and automation experimenters created custom interfaces around it. In later operating systems, security and multitasking made direct hardware access less convenient, but specialized drivers preserved many applications. That long afterlife explains why parallel ports survived in industrial settings after disappearing from consumer computers. A factory may operate a machine for decades. Replacing the machine simply because a new PC lacks an old connector can cost far more than installing an interface card. Legacy ports therefore linger wherever reliability and continuity matter more than fashion. The same is true in laboratories, where an expensive instrument may remain useful long after its original host computer becomes obsolete. In such environments, the parallel port did not disappear because its fundamental electrical role had suddenly stopped working. It disappeared from mainstream computing because newer interfaces offered greater convenience, flexibility, and speed. The distinction matters. Obsolescence often means that a technology no longer fits the larger ecosystem, not that it ceased to function. The parallel port still knew how to do what it had always done. The world around it had changed. Computers became smaller, peripherals became smarter, operating systems became more protective, serial communication became faster, networking reduced the need for direct cables. Users came to expect automatic configuration instead of device-specific setup. USB embodied those new expectations better than LPT ever could. The shift also changed troubleshooting. With an old parallel printer, a user might check whether the cable was fully seated, whether the printer was online, whether the correct LPT device was selected, whether the BIOS port mode matched the peripheral, or whether another device was occupying the connector. With USB, much of that configuration moved into automatic enumeration in software drivers. Problems did not disappear, but the user no longer needed to think in the same low-level terms. This is part of the broader story of personal computing becoming more abstract. Early users often had to understand hardware resources. They encountered port addresses, interrupts, DMA channels, jumpers, and switch settings. Over time, the PC concealed more of that complexity. Interfaces became smarter. Operating systems managed resources automatically. Plug and play became an expectation rather than a luxury. The parallel port sits near the center of that transition because it began in an era of exposed electrical behavior and ended in an era of managed universal buses. Return once more to the back of an old beige PC. The machine is powered off. The monitor cable is disconnected. The keyboard sits nearby. There's the wide 25-pin parallel connector. To a modern user, it may look excessive. Why would a printer need so many pins? Why would a simple peripheral require such a thick cable? The answer is that the port belongs to a different philosophy of computer design. It came from an era when signals were exposed more directly, when hardware roles were specialized, and when sending 8 bits side by side was a practical solution to the limits of contemporary electronics. The parallel port was never elegant by modern standards. It was large, its cables were thick, its distance was limited, its modes became confusing Its performance eventually fell behind newer interfaces. But for decades, it worked. And because it worked, people built an entire ecosystem around it. Printers, scanners, drives, dongles, laboratory hardware, industrial machines, and home electronics all depended on those pins. Then USB arrived, and the old connector began disappearing. The transition represented more than a change in cable shape. It marked a shift in the way personal computers communicated with the outside world. The PC moved away from specialized, hardware-specific ports and toward universal, intelligent, software-managed buses. The parallel port became history, yet its influence remains visible in the expectations it helped create. Users came to expect that a personal computer could connect to external devices easily. Peripheral manufacturers learned that standardized interfaces could create enormous markets. Engineers learned the value of compatibility. Hobbyists discovered the power of direct digital control. The connector itself is gone for most computers, but the idea of the PC as a machine that can reach beyond its own case is stronger than ever. For decades, the parallel port was easy to ignore precisely because it was ordinary. A thick cable left the back of the computer, disappeared behind a desk, and carried data into a printer or some other device. Few users thought about the individual bits moving across its wires. They only cared that the page printed, the scanner responded, or the hardware worked. That ordinary reliability made the port part of everyday computing. Before USB, before wireless peripherals, before network printers, before one small connector could handle keyboards, storage, cameras, audio interfaces, phones, and countless other devices, there was LPT1. There was a wide 25-pin socket. There was a thick cable. And through it, the early personal computer learned how to reach the world beyond its case. The parallel port was large, awkward, limited, and eventually obsolete. But for one long chapter of computer history, it was essential. One final detail helps explain why the parallel port deserves to be remembered. It belonged to a period when the personal computer was still learning what kind of machine it would become. Early PCs were not yet universal appliances. They were collections of specialized parts connected through specialized interfaces. Every new peripheral forced designers to answer the same question. How should this device talk to the computer? The parallel port offered one of the earliest widely adopted answers. It proved that a standard physical connection, supported by firmware and software conventions, could create a dependable relationship between a PC and an entire class of external hardware. That lesson survived long after the connector itself disappeared. USB follows the same broader principle at a far more advanced level. So do PCI Express, Thunderbolt, Ethernet, and modern display interfaces. Their electrical designs are completely different, but the underlying goal is familiar. Define a common language so independent devices can work together predictably. In that sense, the parallel port was not merely a dead-end technology replaced by something better. It was part of the long process by which personal computing learned the value of standardized connection. Its limitations taught engineers what future interfaces needed to improve. Its popularity showed manufacturers how powerful compatibility could be. Its simplicity gave programmers and hobbyists direct access to digital signals, and its ubiquity turned a printer connection into a piece of shared computer culture. When an old PC is restored today and a printer finally responds through LPT1, the moment can feel strangely mechanical and immediate. There's no wireless pairing, no cloud service, no network discovery. A byte leaves the machine, signals change on physical pins, a printer acknowledges the transfer, and paper moves. The entire process is almost visible. That directness belongs to another era, but it is precisely what makes the parallel port such a revealing piece of computer history. It shows us a time when the boundary between the digital world and the physical one was wide, metallic, 25 pins across, and sitting in plain sight on the back of the PC. Its legacy is not the shape of an old connector, but the role it played in teaching the personal computer how to communicate beyond itself. For millions of users, LPT1 was simply where the printer lived. For computer history, it was one of the bridges that made the PC truly useful.